Yeah, okay. Yeah, so thanks. I'd like to thank the organizers for the invitation to be here. I realized it's been so long since I haven't given a virtual talk. I forgot to take the dumb little phone wingding off of my slide, but yeah, I'm happy to be back here, and maybe I'll make up some of my airline status. Okay. Yeah, so today I'm going to talk about a paper that I wrote, I guess posted at the end of May with these collaborators. So most of the sort of pen and paper theory work was done with Paolo Glorioso, who's a postdoc at Stanford, and then numerics were done by another postdoc, Joaquin Rodriguez Nieva, and my student Jinkong Guo. Okay, so hopefully for this audience, I don't need to say too much about what a fluid is. The modern perspective that we have for hydrodynamics is that it's the effective field theory that describes the thermalizing many-body system. Okay, so like in this cartoon here, I imagine I have a big box full of 10 to the 23 different particles, and microscopically they all have some positions and momenta, and there's a lot of information to keep track of. But if we're only interested in sort of measurable questions, things that are sensible on pretty long time and length scales, the idea is that we don't need to keep track of this microscopic junk, and the few degrees of freedom that will survive to long time scales are going to be the conserved the densities of conserved quantities. Okay, and hydrodynamics is essentially a stochastic set of equations that describe the dynamics of the long wavelength modes of these densities. The form of the equations will depend, obviously, on what conservation laws I have, together with any symmetries in the system. Okay, so here I have the sort of textbook Navier-Stokes equations. So I'm ignoring energy conservation, as I'll do for this whole talk, but I have here maybe a mass conservation and then a momentum conservation equation. Okay. And I haven't written down explicitly the form of noise, but one should also think of this as a noisy partial differential equation. The coefficient of my noise is fixed by a fluctuation dissipation theorem. Okay. And those ingredients together form our sort of effective field theory. And in the past few years, we've even learned how to write this down in terms of a sort of two-time action. And so yeah. All right, that's hydro. Sometimes hydrodynamics doesn't exist because the hydrodynamic fixed point is unstable. Okay. And there's a whole zoo of hydrodynamic instabilities, like you push fluid down a pipe and you get turbulent instabilities. That's not what I'm talking about here. Okay. Here I mean that fundamentally, I just have a fluid at rest, not doing anything, and nevertheless it's unstable, and fluid dynamics can't exist.
Did you say it was a fixed point and RG fixed point?
Yeah, so I said fixed point here. That's a deliberate phrase. So for example, if I take this Navier-Stokes system in 1 + 1 dimension, so one space dimension plus time, hydrodynamics doesn't exist because there are relevant operators in these equations, and they flow me to a new fixed point, which lies in the KPZ universality class. Okay. So in this sense, a 1D fluid at rest does not have hydrodynamics. Instead, one finds KPZ. Yeah.
Sorry, I'm very convincing. What is KPZ exactly?
Okay, so KPZ is the Kardar-Parisi-Zhang fixed point. It's a very famous sort of non-equilibrium universality class. It actually has many, many avatars. I don't think this is the original one, but it's certainly my favorite. That's, of course, a sociological comment, but yeah, okay. Any other questions on this sort of lightning review before I continue? So in 2 dimensions, actually also hydrodynamics does not exist. In 2 dimensions, the avatar of this is that if you look, for example, at the renormalized viscosity, you find that there are logarithmic corrections like log omega. And so if you go to low frequency, the viscosity is not well defined. Now in practice, we do atmospheric fluid dynamics. It doesn't really matter, but But as a matter of theoretical principle, a fluid, even in 2D, that does not exist. Not even leading order. Oh, sorry, the question was about marginal operators, or did I miss anything? Yeah, basically, I'll come to this in a little more detail for the fracton fluid, so maybe that will make a little more sense. I'll talk about scaling dimensions and so on in that context. But here I'm going to skip all the details. In a nutshell, there is a sort of sense in which you can have an RG flow for these hydrodynamic equations. And sometimes hydro is the unstable fixed point. Usually hydro is the stable fixed point, but not always. Okay. This talk is about what happens when you have non-trivial constraints and symmetries on the microscopic degrees of freedom. An example of this happens if I demand that in addition to having, let's say, charge conservation, I'll typically be talking about charge conservation today instead of mass just because of my background, but okay. If you have charge conservation, then you can also imagine saying, you know, what if I conserve both charge and dipole moment in my microscopic dynamics? So, okay, I'll say a little bit about realizations at the end of the talk, but for now we're just in theory world. And one way you could imagine this happening is that you have some lattice model and, you know, maybe I have some gas of like low density, you know, particles. Some of them are positively charged, some are negatively charged, but they're all pretty far apart. Okay. In this context, you know, if I look at this individual isolated plus, it can't move anywhere, right? Because, at least not on its own, because if it moves over by one site, then this changes the dipole moment, and that was forbidden because of my conservation law. Okay. So what I can do is I can take, you know, nearby plus and minus particles, and I could move them together. That does conserve charge and dipole moment in the process, so that's okay. If this was a plus charge, then I could have the plus charges sort of repel and move an equal and opposite distance apart. That would also be allowed. Okay. You know, there's lots more pictures I could draw, but hopefully you get the point. This is sort of an unusual microscopic model, but it's well defined. You know, such theories can thermalize. Frank Pullman talked a little bit about this on Monday. And we want to understand the hydrodynamics of a system with this kind of microscopic dynamics. Okay. It's sort of a bit of a popular buzzword these days. We would say that these systems have fracton excitations. The fracton word here means that this individual positive charge is immobile. Okay. It has to move with some other degree of freedom. Okay. All right. So last year it was pointed out that there's a new universality class of hydrodynamics that arises when you have charge and dipole conservation microscopically. Okay. So we were sort of the first to the presses, myself with Rahul Nankishore and Andrei Gromov, but shortly after us, some other authors started to report the same thing. Here's a numerical plot from one of those papers. Very similar to something in Frank's talk, where, you know, we predict that when you have dipole conservation, if you look at the dynamics of the charge density, so I'm not talking about anything other than charge and dipole conservation for now. If I didn't have dipole conservation, the charge density would obey Fick's law, and this would just be the standard diffusion equation. Okay? But in the presence of dipole conservation, this diffusion equation becomes modified and I get this fourth order subdiffusion equation. Okay? And you can see this numerically. This is just sort of a simple scaling check for this prediction. Okay? All right. So I want to say just a few words about where this comes from. Okay. So we're demanding that we need dipole conservation in this theory. Okay? Now, the first thing you might ask is that, well, I have a second conservation law, so therefore I should have a second microscopic degree of freedom. Like I have a density n for the charge density, so maybe I need some new hydrodynamic mode describing dipoles. But that can't happen. You could not have that degree of freedom, because if you have a sort of little bound dipole state, it can be absorbed and emitted by other charges. So sort of bound states of dipoles are not a conserved quantity, okay? Only n can be a hydrodynamic mode. Instead, what dipole conservation does is it puts a constraint on the form of the charge conservation equation, okay? So if you just imagined that you had the usual charge conservation equation, this was just divergence of a current J. If you plugged it into this identity, you would find after integrating by parts that you had an equation that couldn't always be satisfied, okay? So the only way that you can sort of always make sure that independently of the microscopic details, dipole moment is conserved is to demand that the current comes with these two derivatives, okay? If you want to get sort of fancy and you like field theory, you can think about this as the density couples to a sort of time-like component of a gauge field, whereas the second rank current, Jij, couples to a second rank tensor in spatial indices. And these are precisely the kinds of constructions that show up when people talk about this kind of funny electrodynamics of fractons. Okay, this is sort of maybe, for me at least, a more physical realization of that same idea. Okay, lastly, demanding consistency with fluctuation dissipation theorems, we learned that you are not allowed to write down a zero derivative term in Jij. Okay, not possible. The first thing you can write down has two derivatives, just so that this Cij, the noise, is local in this second rank object. So this Cij will have some white noise variance. And anyway, you put all these ingredients together and you get this fourth order subdiffusion equation. There's a whole zoo of these universality classes if you conserve additional multipoles and subsystem symmetries and so on. I don't really want to say too much about this whole landscape, but you can read about some fraction of it in our paper. Okay. This talk is sort of motivated by the desire to understand a kind of playful question, which is, what happens if you take one of these exotic fluids that has both charge and dipole conservation, but you also add one of the sort of old school conserved quantities as well, which is momentum, okay? Remember that what makes an ordinary fluid so exciting is that we have, let's say, both mass and momentum conservation. If we had just had mass conservation, we wouldn't be flying planes, we would just have diffusion everywhere. So it's important that we have, both mass and momentum conservation to make fluid dynamics sort of interesting. And so, as a playful question, we could ask, what happens if you try to add dipole conservation to the Navier-Stokes equation? Sort of how much of a wrench does that throw into the story? Now, one of the motivations to take this idea a little more seriously is that from the field theory perspective, it turns out that these fracton models, I guess if I go back a few slides, those fracton models turn out to sort of not play so nice with conventional constructions in field theory. So there's some value in understanding, how to build a hydrodynamic field theory for fractons. A particular motivation is that if you ask what are the sources that momentum couples to, if you have a conserved momentum, you should have a stress tensor in your theory. The stress tensor couples to gravity, and in principle, if we know how to build an action for hydrodynamics with dipole conservation, we might learn something about how to couple fractons to gravity, at least, to some kind of silly curved spaces with funny coordinates. So this is sort of a longer term goal. We're not there yet, but this is some motivation for actually taking this sort of cartoon problem seriously. Okay. So with that, we dive in, and let's sort of first just, get a grasp on the basic setup here. So in the hydrodynamic limit, okay, I have a long wavelength theory, or I'm after a long wavelength theory rather. The degrees of freedom in this theory are going to be the density, charge density little n, and the momentum density little pi, okay, coming with a vector index, of course. The conserved quantities are the total momentum, the total charge, and the total dipole. And there's an algebra relating these coefficients, which is called the multipole algebra. This is sort of the simplest manifestation thereof. And what we find is that the Poisson brackets, or commutators if you multiply by I, of momentum and dipole with charge both vanish, so these are kind of boring. But dipole and momentum do not commute. Their commutator gives us charge. And this last commutator is what makes hydro fun, okay? And a lot of work to figure out what's going on, okay? All right. Any questions at this point on the setup?
I can answer the question.
Sure.
So if you go back a slide, when you wrote the equation for when you write the equation for conservation of momentum, say typically I think of the first term and the term with BI/VJ appear in that combination because of boost invariance, essentially. So
Yes.
I need to have some like a Fisherman derivative acting on V.
Yes.
On the other hand, I think conservation of dipoles by themselves, is that compatible with boost invariance?
So I do not believe that, so the question, right, is can you have some kind of boost invariance, et cetera, with dipole? I think the answer is no. So the fluid we're going to see is certainly not boost invariant, but that doesn't mean it's not well defined. It's perfectly happy, it just doesn't have boost invariance.
No, that's okay, but so maybe, will you use the second equation there? If so, should it have a more general form?
I'll show you what happens. It's actually much worse than this. So things get a lot more exciting than just some simple change to these equations. But
okay.
That's sort of my next point.
Okay.
Okay. So with that segue, so what do we expect to see? So we know from before, right, that the hydrodynamic equation for charge density is going to depend on two derivatives. We're not just going to have a current with one derivative, but the local object is Jij, so everything in this charge conservation equation has to come with two spatial derivatives. So immediately we know, right, that we can't write down a sort of usual looking mass conservation equation because that would not be possible. That term doesn't have two space derivatives. A priori, the momentum equation though might look kind of standard. You know, momentum a priori doesn't have any moments conserved. If we have rotational invariance, then you'd have angular momentum, but let's not worry about that. That's sort of a technical thing. Okay, so we're trying to find some constitutive relations for J and T. Namely, we're asking, how can you write J and T as functions of pi and n in such a way that the theory is invariant under essentially the multipole algebra and objects transform nicely. And then, of course, we also want a fluctuation dissipation theorem, a second law of thermodynamics, and so on. Okay. Now, the first sort of awkward thing that you notice is that if you ask how the momentum density transforms, because momentum and dipole don't commute, you get this really bizarre transformation law, where if you, I think maybe an easy way to think about this is take the momentum density operator in a quantum many-body system and conjugate it by the dipole operator, the global dipole operator. Because that's a conserved quantity, this is a very benign thing to do physically, but it's not benign on the operator. I mean, it actually gives you this kind of funky term where pi shifts by a constant vector times the charge density, okay? And so the theory must be invariant under this kind of shift, which is pretty weird. But the way we handle this is we say that, you know, the thing we want to talk about in our thermodynamics is not momentum density directly, but rather a little v velocity, which is pi divided by n, okay? And we're demanding that this theory cannot depend on the actual value of v. It can only depend on gradients of v, because the dipole algebra allows us to arbitrarily shift the value of v. That's an unphysical change, okay? So we conclude, for example, that if we look at something like entropy density, that can only depend on density, charge density n, and then gradients of this little v velocity. Now you turn the crank, and there's some algebra, and it's really messy, and at the end of this, you find this kind of funny set of equations. So your second rank current, so here T, capital T, is just a sort of fixed temperature set by noise. It's not playing much of a role in our story. But yeah, we have expressions for J and T. Note that we have a capital V velocity, which is different from the little v velocity. Okay, sort of a technical thing, but this capital V is actually the conjugate to momentum, so that's what shows up, for example, in the analog of viscosity. So anyway, we have ideal hydrodynamics. We thought about first order dissipative corrections. There's noise and a fluctuation dissipation theorem. And all right, if you take, all the equations on the last two slides and you cram them all together, you get our effective field theory with charge and dipole conservation. Okay. Cool. So at this point, let's now ask, is hydrodynamics actually a stable theory? So if we were studying ordinary Navier-Stokes equations, we could ask, are these equations actually stable in the RG sense?
Sorry, did you write down a Gaussian theory that you're going to compute the power counting around? I didn't see that.
Okay. So the question is, what are we power counting around? So that's a good question. We're going to power count around linearized hydrodynamics. Okay. So we can take these horrible nonlinear equations and we can perturb around just uniform density and constant pi. And when we do that perturbation, we find that this theory should have a scaling dimension z equals 4. I'll comment on that more in 1 minute or so. And we find scaling dimensions for noise and then the conserved densities n and pi. Okay. Now, let's consider sort of what seems like the most dangerous nonlinearity, which is the one coming from pressure. Okay? If we look, for example, at this linear term in pressure, it actually is a priori relevant. Okay? But the reason we don't count this is that if we throw out everything else, this is not a dangerous, right? It's not a dangerous thing. It just means that rather than just having something subdiffusive, we have something subdiffusive that propagates. In KPZ, this is actually a little bit nicer. For the ordinary fluid, you would have a linearly propagating sound mode, like omega is of order k, and so you could just boost to the wavefront's frame and make this term go away. Here, it's not quite that simple because we actually have modes that propagate with k-squared dispersion, sort of like magnons, and that's not entirely accidental. Okay, anyway, so this term we kind of ignore. It's not a big deal. Linear hydro is perfectly well behaved. But we can ask, when is this quadratic correction in pressure a relevant operator? If this one isn't irrelevant, it's kind of scary because it gives us a nonlinear stochastic PDE. We're definitely not going to know how to solve that one. And we find that this term is relevant below 4 dimensions. Okay? So essentially, the addition of dipole conservation raises the upper critical dimension of the KPZ universality class, or this manifestation of it at any rate, from 2 to 4. Okay? And so, in no physical dimension would a dipole conserving fluid actually exist. It would flow to some other non-equilibrium universality class that I'll call a dipole KPZ fixed point. Okay? And kind of this is our punchline. So any questions on this part before I move on?
So maybe there is no relation, but can you comment if there is a connection to model B, which has the same dynamic exponent?
So, okay, maybe this is embarrassing, but I don't remember the sort of numberology of Hohenberg and Halperin, so maybe we can talk about this offline. But
you said something about there not being, about the connection to magnons not being entirely coincidental. Do you want to?
Yes, I'm going to come to that right now, actually. Yeah, okay. So for the last part of the talk, I want to talk a little bit about, what's the whole point of this? Like, is there actually any point to this exercise at all? And, okay, at least some motivation for doing this is that, in principle, these are actually numerically accessible universality classes. So what I'm showing here is a Hamiltonian model for a one-dimensional system that actually will realize a fluid with charge and dipole and momentum conservation all in one. Okay? So how does it work? Well, I have this kind of funny kinetic energy term, right, where it's not p squared over 2, like an ordinary fluid with particles of mass 1, but this one has a kinetic energy that depends on the difference of the momenta. Otherwise, it's sort of usual, right? I've got maybe some nearest neighbor interactions and, okay. Now, you know, we would teach to our undergrads, right, taking Lagrangian mechanics that, or Hamiltonian mechanics, I guess, the reason why this Hamiltonian, right, has momentum conservation is that if you shift all of these coordinates xi by a constant, the Hamiltonian doesn't change, okay? So this means you have momentum conservation. It guarantees this property. Now, in this Hamiltonian, right, we also have invariance under a shift in the sort of conjugate momenta pi. And so if you think, what is the conserved quantity that that is going to guarantee? It's the sum of all of the xi. And that is just another name for the dipole moment of the theory. So this is a simple argument that this microscopic Hamiltonian must conserve dipole moment along with momentum, okay? So again, I'm so sorry, Bert, but I don't know any of your, you know, letters and numbers and so on. So we just called this one Model A, okay? This is our dipole KPZ Model A, okay? And we can add dissipation and noise to this model if you want in such a way that preserves these shifts. And when we do that, okay, we have a system with the desired conservation laws. We can just throw it on the computer. And I'll show you in a few minutes what those simulations give us. But let me now come back to this Magnon relation. So if I take the, let's say, this simple Hamiltonian for the Heisenberg ferromagnet in just a 1D chain, let me imagine that this system, you know, although the ferromagnet doesn't exist in 1D, within linear response, I can just say, let me put all the spins to point in the z direction and perturb around that, right? And I get a theory of propagating magnons. And it turns out that within the linearized version of this ferromagnet, you can think of Sx as analogous to dipole conservation, Sy analogous to momentum, and Sz is analogous to Q. And again, just within linear response, it actually exactly maps onto this Hamiltonian. So this is sort of a pretentious way of understanding the k-squared dispersion relation of magnons. It really comes from this sort of emergent dipole and momentum conservation within linear response. Okay. All right. There's another model that we thought of simulating to try and look for this breakdown of hydrodynamics. And this is a model where dipole and momentum are both emergent conservation laws. This model is actually motivated by an experiment that took place 2 years ago. There was an experiment where a bunch of fermions, you know, given or described by the Fermi-Hubbard model, are thrown into an optical lattice, and then you just take the lattice and you tilt it. And when you tilt it, you know, what happens, each of these fermions, right, has a finite kinetic energy because we're in a lattice, so there's some bandwidth. But there's a lot of energy, you know, coming from the fact that these are tilted fermions, so there's just gravitational potential. So you can only, you know, if you just had one fermion in the system, it would fall down some distance in the lattice and then get stuck. Okay, just energetically, you couldn't give it any more kinetic energy. So, and in this system, I should add, when you put lots of fermions in it and you let them interact and you ask how do charge fluctuations decay, you actually see that, you know, when the tilt is big enough compared to the size of your experiment, you actually see fourth order subdiffusion. And this is precisely a consequence of the charge plus dipole conserving universality class from before. So our idea was that maybe we can take a sort of classical continuum version of that story, okay, with sort of fast block oscillations coming from this cosine kinetic energy, and we'll superimpose that on top of, or rather we'll add interactions on top of that picture, and let's see what happens. Okay, so we take each one of these two models and we throw random initial conditions into it, okay, and then we just let the system go. Now, if this were a fluid that, you know, it was nice and hydrodynamics made sense, we would know exactly what happens, right? The hydrodynamic modes have decay times that scale as 1 over k to the 4, because remember z equals 4 in this model, okay? And if I just sort of invert that formula around, I would guess that the typical wave number of correlations in my model should decrease with time, and it should scale as time t to the minus 1 over z, where z is my dynamical critical exponent. Okay? Now, we can actually tune the potential in our model to basically turn on or off this quadratic nonlinearity in pressure. When we turn it off, we run this simulation and we find that the dynamic critical exponent is approximately 4. Okay, so that's pretty close to our original prediction, and it seems like if hydrodynamics doesn't exist, it sort of almost exists. The instabilities are pretty mild if they exist at all. We think they do, but we can't resolve them. However, when we do turn on this quadratic nonlinearity, we find that the decay, ramps up quite substantially. And if we try to estimate what is the dynamic critical exponent of this model, it turns out to be 2.5. This number makes us happy because it turns out there's a very sort of simple scaling guesstimate. And if you try to guesstimate that you should determine z not by balancing dissipation and all the other terms in your equations, but by balancing this convective sort of nonlinearity with all the other terms in your equation, you get z equals 2.5. Apparently, the same argument does get z equals 1.5 correct for the KPZ universality class. So anyway, this is kind of an interesting observation. Read into it what you want. Anyway, we do believe that these models independently are accessing the same fixed point with approximately the same exponent, and we believe this is pretty reasonable numerical evidence for this new universality class. Okay. All right, so with that, let me wrap up. So we found a new non-equilibrium universality class dubbed Dipole KPZ. Name it something else if you want, I don't care. This is one of an infinite new zoo of universality classes. I'm just showing you one of them, but you can find analogs of these fluids where the upper critical dimension is as large as you want. Okay, so there's a whole zoo, a new landscape to explore. I think one of the reasons this is worth exploring is that this whole zoo of fracton fluids is sort of stress testing the conventional Landau paradigm for hydrodynamics that I think has guided us for almost a century at this point. And in particular, when we start breaking symmetries like time reversal and inversion, this is ongoing work, but it really sort of starts to stress test the Landau prescription of what terms you're allowed to write down and which ones you're not. And I think if we understand these fracton fluids and their field theories, we'll ultimately end up with a much deeper understanding of what hydrodynamics is. And then I mentioned before, we're slowly working on writing up the field theory version of this story, even less friendly than this one. And once that's done, I hope that we'll be able to understand a little bit more about how to couple fractons to gravity. That's sort of a question maybe not so interesting to this audience, but I think there are other audiences that would care about that. All right, that's all I wanted to say. Thanks. All right.
A couple of questions. One, so I usually think of the quadratic dispersion relation of magnons in ferromagnets as arising because the ground state breaks time reversal. So in this case, I couldn't see any time reversal here. So
time reversal is conserved in this Hamiltonian, but the point is just if you take this Hamiltonian H and you write it, so the fluctuations at leading order around the ferromagnetic ground state would just be delta Sx and delta Sy. And if you just take this Hamiltonian and expand it to quadratic order, you get exactly this one. So that the point I'm making is nothing more or less than that.
Okay. And then the other question I had is, you neglected, I think, energy conservation for your talk, and I was wondering whether that, how that would change the picture.
Okay, so strictly speaking, if you put energy conservation back in, we've done this from the field theory perspective, and we believe that this actually ruins this universality class. It makes Z equal to 2 again, and this is just because there's no dipole for energy. So it anyway. It actually turns out we cannot see this at all in numerics. it seems like both with no noise and with weak noise, it seems like Z is sort of kind of similar. It's around 2.5, and so yeah. But we do think that, strictly speaking, if you have energy, it does change the universality class here. So unless you're at some like infinite temperature-ish point where you can sort of forcibly decouple energy diffusion from these other modes. If you can do that, then this fixed point can survive.
Okay, then if not, let's thank Andrew.